Welcome to The Explainer. Today, we are diving into a really cool discovery that's shaking up how we think about quantum computers. It all comes from a paper that proves, for the very first time, that a quantum computer's real magic might not be in finding neat little patterns, but in taming pure unstructured chaos. Right, so we always hear the stories about quantum computers breaking codes by finding these hidden mathematical structures. But this new research poses a way deeper question. What if their biggest advantage isn't about finding order at all? What if their power actually shines brightest when there's no order to be found, when it's dealing with pure randomness? Now, to really get why this finding is such a massive deal, we gotta take a quick step back and look at the traditional search for what we call quantum advantage. That hunt for problems where quantum machines just absolutely leave classical computers in the dust. If you look back at all the greatest hits of quantum computing, from Peter Shor's legendary factoring algorithm back in '94, all the way to recent experiments, you'll notice they all have one thing in common. Every single one of them was designed for a very specific type of problem. And that common thread is structure. You see, these incredible algorithms are basically pattern-finding geniuses. They're designed to sniff out and exploit these deep mathematical regularities, kind of like a brilliant detective who can spot clues at a crime scene that no one else can see. So this total reliance on structure leads to a huge, lingering question. What happens when there are no patterns? Is that structure a deal breaker? Is it absolutely essential for a quantum computer to get that game-changing, super polynomial speed up? And, that's the kind of leap that takes a problem from impossible for a billion years to done in 5 minutes. Can you make that jump without any clues? Just think about it like two completely different universes. In one, you've got your structured problems. They're like perfect, beautiful crystals. They have an internal logic, repeating patterns. But in the other universe, you have unstructured problems. And these are like pure random TV static. There are no shortcuts, no secret patterns, just chaos. In computer science, we actually have a perfect theoretical model for this kind of chaos. It's called a random oracle. Just imagine a magical black box. You can feed it any input you want, and for every single one, it spits back a completely, truly random output. There's no rhyme or reason to it. It is the ultimate mathematical version of a structureless problem. So the big question was, do quantum computers still have that game-changing edge in this land of pure randomness? For decades, the general thinking was, probably not. The belief was that, a quantum computer might be a bit faster, but a classical one could still, theoretically keep up. There was no true, unbeatable advantage to be found. Well, that long-held belief just got completely flipped on its head. In a 2024 paper, researchers Takashi Yamakawa and Mark Zandri proved something that, frankly, a lot of people thought might be impossible. Okay, so here's the core of what they found. They basically designed a special kind of puzzle. It's what's called an NP search problem, where the answer is super easy to check if you have it, but insanely hard to find. And what they proved is that a quantum computer can solve this puzzle, no problem, but a classical computer is mathematically guaranteed to fail. This is that massive super polynomial leap we were talking about, and for the first time ever, it's been proven to work without any hidden structure at all. And right at the heart of this whole thing is this really clever cryptographic puzzle. It's built in such a way that a quantum computer can crack it, but it's just completely impossible for even the most powerful supercomputer we could ever build. So solving it becomes the ultimate proof that your machine is genuinely quantum. This is what's called a proof of quantumness. So imagine this. A quantum computer, the prover, finds the answer to this special problem. It then hands that answer over to a regular old laptop, the verifier. The laptop can easily check if the answer is correct. And if it is, well, the laptop then knows with absolute certainty that the answer could only have come from a machine harnessing the power of quantum mechanics. Okay, so how in the world does a quantum algorithm solve a problem that has a zero structure? How does it find a needle in a haystack that's not just big, but completely and utterly random, with no clues at all? So let's break down the challenge. Imagine you have a huge set of secret keys. We'll call them code words. Your job is to find the one single special key that when you feed it into our random black box, it spits out a very specific result. Let's say a string of all zeros. Now, classically, your only move is to try every single key, one by one, which would literally take forever. But the quantum way of thinking is just totally different. First, instead of trying keys one at a time, it uses superposition to hold all possible keys at once. Then, and this is the genius part, it applies a special mathematical lens called the quantum Fourier transform. Think of it like switching your view from a regular map to a satellite image that shows heat signatures. It just reveals a whole new layer of information. In this new view, the one correct answer actually creates a tiny, faint signal. The algorithm then brilliantly amplifies that one signal, while all the other random noise just cancels itself out. Then you just measure the result, and bam, the one correct key is all that's left. So why is this so important? I mean, this isn't just one cool new algorithm. This is a fundamental discovery that literally reshapes our entire map of where quantum power even comes from. The implications here are huge. For one, it proves the chasm between what classical and quantum computers can do is even wider than we thought. It also gives us a recipe to cook up new kinds of cryptographic puzzles that are provably unbreakable for regular computers. And crucially, the proof is something anyone can check on their own laptop. This is a massive step up from older experiments that were really hard for anyone to verify. It's like a quantum computer performing an impossible magic trick, then handing you the blueprints to prove it wasn't just smoke and mirrors. At the end of the day, this is a major first. For this whole family of hard-to-find, easy-to-check problems, this is the first time we've seen a massive quantum speedup that doesn't rely on that old trick of finding repeating patterns, which is how Shor's algorithm works. It proves there's an entirely different source of quantum power that we're just now starting to understand. And that just leaves us with this incredible, mind-bending thought. For decades, we've been looking for quantum advantage in the clean, elegant patterns of mathematics. This paper shows us it can also be found in their complete and total absence. And it makes you wonder, what other amazing computational powers are still out there, hiding not in order, but in the heart of chaos itself?